Welcome to my talk ArrayQL for linear algebra within Umbra. The motivation for this paper was in database machine learning using ML to SQL, a declarative meta language that translates to either SQL or Python. But the problem was that always the data was first converted into arrays, which is expensive. So the goal of this work is to work directly on arrays. So the solution is to implement ArrayQL, an array query language inside of a relational code-generating database system. The structure of this talk is as follows. First, we will present the ArrayQL algebra, where we completed its syntax draft, added statements for joins and for temporary tables. Then we proceed with the Umbra integration, where we first implement ArrayQL inside of a code-generating database system, and then we explain the relational representation. So the ArrayQL algebra is known to be a data definition language to create arrays as new arrays or out of an existing array. Furthermore, it is a data query language composed out of select, from, where, and a group by clause for the indices for the dimensions, as well as attributes like arithmetic expressions. Then we need the source array, then we can filter entries by a predicate, and afterwards we can group the arrays by the dimensions that should be preserved after an aggregation. What we added to the ArrayQL algebra is temporary arrays and joins. So temporary arrays are introduced with and joins are indicated by a join keyword. Also, we extended its use as a data modification language to update specific cells of an array. For about the Umbra integration, we should know that it is a code-generating database system that follows the producer-consumer concept. How it works is like that. First, it expects an SQL as input, then it generates an abstract syntax tree, then the semantic analysis happens, and afterwards code is generated. If we want to add another language, we have to add another grammar file, and we have to add another semantic analysis. But in the end, it will be compiled together. As only the schema is known during compile time, and not the values, we need a relational representation, which I will explain in the next slide. So the goal is to have a uniform representation that allows access from SQL and an array query language. So here's the matrix, and possible is either a coordinate list, which is a relational representation, or a table added by a row ordering. The relational representation saves memory for sparse arrays, and primitive data types are sufficient even for more than 2 dimensions. So what we do is we have an n-dimensional array with m attributes that is translated into a table with n plus m attributes. Attributes for the indices are unique and form the primary key. Furthermore, ArrayQL has the terms bounding box, validity map, and content. At the creation, we insert 2 tuples, defining the bounding box between upper and lower bound. An entry within the bounding box is valid if it exists and at least one attribute is not null. We can now map relational algebra to ArrayQL algebra. ArrayQL has 9 operators, and we all translated them into relational algebra using the underlying scheme. One relation of indices and attributes are translated into a schema, with all being an attribute. And the coordinates form the primary key and delimit the bounding box. The validity map of an array can be displayed as the set of indices of all valid entries. For example, we have an inner dimension join, which is translated into an inner join. Combine statement is translated into a full outer join. A filter operation is of course translated into a selection. we can now use ArrayQL for linear algebra. The bounding box defines the size of a matrix. The attributes determine the field of which each entry is a member, for example, floating point numbers for real numbers. Scalar operations are part of the select clause. Matrix operations belong to the from clause. For sparse matrices, values of non-existing entries are assumed to be 0. That's different to a normal usage of ArrayQL, where we introduce the keyword filled behind select to indicate the use for linear algebra. We introduced shortcuts for matrix operations as part of the from clause. Like that, we can translate linear regression simply into one statement, part of the from clause. Let's come to the evaluation. We evaluated on a Ubuntu machine with 6 CPUs and 62 GB of main memory. We varied either the number of elements in a dense array or the sparsity. When varying the sparsity, grammatrix computation happened on a resulting matrix of 90,000 entries. Matrix addition was performed on each array having a size of 10 to 6 elements. With increasing size, ArrayQL computes the matrix sum faster than RMA. MATLAB matrices and Umbra benefit from sparse matrices because they are using a relational representation. To summarize, a relational representation shows comparable performance to existing database extensions for linear algebra, like RMA and MATLAB. To conclude, this talk presented the first ArrayQL integration. This was integrated as another query interface and was addressable inside of SQL. Integration was done into a code-generating database system, namely Umbra. We introduced a relational array model and mapped SQL operators to ArrayQL operators for a translation into relational algebra. In summary, ArrayQL in Umbra benefits from sparse matrices as well as the performance of an in-memory database system. Thank you for your attention.